So today's lesson, we're going to continue looking at gases, and let's start with what we call a heating curve. All right, and if we were to draw a heating curve, our temperature in degrees Celsius is going to be our y-axis, and our energy is going to be the x-axis, and sometimes you'll see it written as time, okay, because the energy being supplied over time. And our heating curve is going to look something like this. Where we have a solid, we have a liquid, and we have a gas. And if this is the heating curve of water, we know that at 0 degrees Celsius, my solid ice becomes liquid water, and we call that melting. So through this phase change, I am going from a solid to a liquid. So at this point, I am all solid. At this point, it is all liquid. And there's a process where we have solid and liquid at the same time. Think about it. If you put ice in a cup, it doesn't just poof, magically become liquid water. You end up with some ice, some water. All right. So here's my liquid. And we know that a liquid water will at 100 degrees Celsius become a gas. So at this point, it is all liquid. At this point, it is all gas. And the process at which we go from a liquid to a gas, we call vaporization. And through this process of vaporization, I have liquid and I have gas at the same time. Okay, so we start all liquid, we end all gas, but at some point we have both liquid and gas. Okay, and so if we look here at our solid and our liquid and our gas, a couple of things are changing. The amount of energy being provided is changing, and so is the temperature. So temperature is the measure of the average kinetic energy within a substance. So solids have kinetic energy, liquids have kinetic energy, and gases have kinetic energy. Now, at the process at which we melt, my temperature remains constant, and the process of vaporization, my temperature again remains constant. So my temperature is not changing, but what is changing? The amount of heat energy being added. So as I melt, the amount of energy is increasing. And for my vaporization, again, the amount of energy is also increasing. So I'm adding energy, but it is no longer changing the temperature. So where is that energy going? All right, and so that's kind of what we're looking at here. Let's think back. You'll remember solids are particles really close together, and liquids are particles that are somewhat further apart, but not quite all the way apart. And in a gas, particles are very far apart. Okay, so where is this energy going? When I go from a solid to a liquid, I am changing the spacing of particles. All right, so what kind of energy is related to the spacing of particles? And that is potential energy. When I go from a liquid to a gas, I am changing the spacing of particles even more. So again, vaporization has potential energy. So this energy is no longer being used to increase the temperature. It is being used to break the intermolecular forces during this melting process to take my particles from close together to further apart. And the same thing is happening when I go from a liquid to a gas. So a liquid has less intermolecular forces, and we see that because our particles are further apart from each other. However, in a gas, all intermolecular forces have been broken. So when I vaporize something, my temperature remains the same, but my energy increases. That energy is being used to break the remaining intermolecular forces during vaporization. And if you'll remember, we said most gases behave as an ideal gas, and ideal gases have no intermolecular forces. So let's talk real quickly about two vocabulary terms that tend to trick students up. All right? Vaporization and evaporation. All right, so at this point, you may have had science teachers who use these two words interchangeably, but the reality is we're doing you a disservice. Vaporization is not evaporation. They both go from a liquid to a gas, but what is the difference? Vaporization is a liquid to a gas, but it occurs at the boiling point, which for water is 100 degrees Celsius. Evaporation is still a liquid to a gas, so this is how they are the same, but it occurs below boiling point. If I was to take a glass of water and sit it out and come back to it next week, is the water still there? No, it has evaporated. The temperature of my classroom is not 100 degrees Celsius. All right, so evaporation is happening at the surface. All right, some particles have enough kinetic energy that they are able to break away and go into the gaseous form. All right, but it is happening below boiling point. So when we talk about vaporization, it is at boiling point. Evaporation is below boiling point. I need you to please use those two words correctly. All right. So substances can heat up, but I can also take gaseous water or any other substance and I can cool it down. So let's look at a cooling curve. A cooling curve is the opposite of a heating curve. All right, we still have temperature over here on the y-axis, and we still have our energy on the x-axis, but instead of heating, we cool. All right, so here's my solid, here's my liquid, and here's my gas. Now, when I go from a gas to a liquid, that is called condensation. And when I go from a liquid to a solid, that is called freezing. At this point, the substance is all gas. At this point, the substance is all liquid, but there is a process in which it goes from the gas to a liquid. So at some point, we do have gas and liquid at the same time. We are bringing our particles closer together. We are changing the spacing of those particles so it has potential energy. At this point, the substance is all liquid. At this point, it is all solid, but it is a process where I go from a liquid to a solid, so I will have liquid and solid in the substance at the same time. Again, I am making those particles closer together, so again, potential energy. My gas, my liquid, and my solid are all changing temperatures, so we say they have kinetic energy. And at this point, we've kind of reviewed pretty much everything that you probably already learned from previous science courses. One additional thing which you may or may not know, it is possible to go directly from a gas to a solid without passing through the liquid phase. And we call this deposition. And this is what causes snow to form. Gaseous water in the atmosphere goes directly to a solid. This is what gives snow the properties that it has, that fluffy part. All right. This is why it is significantly different than sleet. Sleet happens when gaseous water goes to a liquid, and then that liquid freezes into solid water, which we call ice. Freezing rain is when liquid water hits the surface of the earth and turns into a solid. So if we can go directly from a gas to a solid, we can also go directly from a solid to a gas without passing through the liquid phase, and we call this sublimation. An example of this is dry ice. Solid carbon dioxide will form directly into gaseous carbon dioxide, and this is the smoke you see, the smoke looking stuff you see if you've ever seen dry ice. What you're looking at is that process of sublimation. All right, so let's talk about vapor pressure. Vapor pressure is the pressure exerted by a vapor at equilibrium. When it's with its solid or liquid at room temperature. All right. So why does vapor pressure increase as temperature increases? All right. And this is going to go back to a worksheet that I have provided for you on the website. All right. Temperature versus vapor pressure curve. So you may want to pause this video, go look at that vapor pressure, take a moment and look, and you will notice that as the temp is down here, as the temperature increases, so does the vapor pressure. All right, so go take a look at that. Come back to this video. All right, so as temperature increases, more particles have enough kinetic energy to become a vapor. Right, because temperature is the measure of average kinetic energy. So if I have a higher temperature, I have more kinetic energy. The more vapor, the more collisions. And remember, pressure is a measure of how many collisions. The more collisions we have, the higher the pressure. So if I increase the amount of vapor, I increase collisions. Increasing collisions causes an increase in pressure. All right, so the more vapor, the more collisions, and the more vapor pressure, P for pressure, and then I wrote out vapor, will increase. All right, so let's look at two vocabulary terms. Volatile. It would help if I could spell it correctly. Volatile. A substance that is volatile evaporates easily. It has a low boiling point. BP for boiling point. It has a low boiling point. It has weak IMFs, intermolecular forces. Because the intermolecular forces are weak, not a lot of energy is required to break those forces, allowing it to evaporate easier and therefore giving it a lower boiling point, the temperature at which it boils. Some examples would be methane and rubbing alcohol. All right, if you've ever used a thermometer to take your temperature, you may have gotten some rubbing alcohol and cleaned that thermometer, and you've noticed that it doesn't take too long for all of that alcohol to evaporate off, making it safe for you to then put the thermometer inside of your mouth and take that temperature. The opposite of volatile is non-volatile. Okay. These substances do not evaporate easily. Therefore, they have a high boiling point. Okay, BP for boiling point. And now that makes sense. If they have a high boiling point, then that means they have a lot of energy needed to break intermolecular forces. Therefore, they're not going to evaporate easily. So that would also stand to reason that they have strong intermolecular forces. All right. So one more thing that we're going to look at, and that is a phase diagram. And now this phase diagram you already have, all right, is the phase diagram section of that worksheet I provided for you on the website. Okay, so in this phase diagram, our pressure, and in this particular example, it is in atmospheres, is the y-axis. Our temperature is the x-axis, all right? And our phase diagram has a couple of different things that we can look at, okay? Now, atmosphere, we know the standard atmospheric pressure is 1. So this point right here is standard atmospheric pressure. But as I change pressure, or as I change temperature, or both, I can adjust the temperature at which something will move between phases. All right, so from here to here, okay, that's labeled A on your thing, and this is a solid. All right, so let's just color these in. I'm just going to give y'all a visual representation here. Sometimes colors are a good way to do that. All right, so this substance is a solid in this entire section. All right, in this section, which is labeled C, it is a liquid. So I'm going to go with pink. Okay. All right, so this section right here, these substance is all a liquid. And then down here, this substance in section B is going to be a gas. And let me choose, I'm going to go with, I'm going to go with brown. Trying to choose colors here that if you are colorblind, you can still see. Okay. All right, so hopefully these colors show up for you. All right. So When I go from a solid to a liquid, we call that melting. So this line right here is melting. If I go from a liquid to a solid, we say that is freezing. So this line is also freezing. When I go from a liquid to a gas, as I go across, that is vaporization. If I go from a gas back to a liquid, that is condensation. All right, so right here is my vaporization condensation line. And then finally, if I go from a solid to a gas, that is sublimation. A gas back to a solid is deposition. So this is my sublimation deposition line right here. All right, now it's really important to note there's a couple of other things that we can learn from this. So this point right here is called the triple point. And the triple point is the point in which all three phases exist in equilibrium at the same time. Would help. Spelling is not going well for me today, is it? Okay. Exist. So it is possible at a certain temperature and a certain pressure to have a solid, a liquid, and a gas at the same time. So that is our triple point. This point right here, we call this the critical point. And the critical point is the point at which a phase can no longer occur, a phase change can no longer occur regardless of temp or pressure. All right. So we have our critical pressure, the pressure at which the critical point occurs. And we can also therefore have our critical temperature, the temperature at which the critical point occurs. All right. So one additional thing, let's check out this slope of this line. This is my line that brings me from a solid directly to a liquid or a liquid directly to a solid. So this is my freezing and my melting point. Check out the slope of this line. This slope is a positive slope. So from this positive slope, we can actually tell that the solid is more dense than the liquid. All right, so from the slope of the line, we can determine the density of that solid compared to the density of that liquid.